Hmm.
I always like to start with this slide because people often ask what is happening with the club, and you can find out on our website calendar found there at the QR code or the website address. On the same main facing homepage is also the IO groups option at the bottom. There you can find updates for activities that are happening. You can ask questions. You can search archives to find out if your question has already been addressed. It's a really great resource for club members. We also have a YouTube channel. We have a Facebook site where you can find a lot of astrophotography. It's fun to look at. And then also an Instagram page. I do want to mention a couple quick calendar items and highlight them. First of all, if you check the chat, you can see that a very popular event that a lot of club members participated in this year is the Grand Canyon Star Party hosted by the Tucson Astronomy Club. So how do you become a part of this awesome big event where you can actually camp inside the national park gates? Is to get on the mailing list. This won't allow you to register just yet. You'll have to wait until February to do that. But if you check out the email and sign up, you'll get early notification to register for that event. So if that's something you're interested in doing, and go ahead and check out the program when our members were highlighted for that trip. It looked like a ton of fun. The information is in the chat. Also, I want to mention that we're coming up to the tail end of our meetings for the calendar year, and that next month is our really popular and fun gadget night. We're working on a fun venue that's central to everybody, much like the big reveal was in Miramar. That was a pretty popular location. The date is November 20th. And for those of you who haven't attended gadget night, what does that mean? And really, it's an open mic night. So I know already that some of the topics we'll be sharing are how you can show up to a star party or just a gathering with friends and not have a whole lot of complicated equipment. In fact, it's pretty simple what you need to bring to carry out the mission of our group, and that is outreach, to share the night sky with people who may not have seen it before or know what to do. We'll also be highlighting different power banks and what they do and what they cost. If you aren't familiar with power banks to run off the grid, we're also going to be talking about even if you have a favorite story to share of how you got into astronomy, or your scariest or funniest time at a star party. We want to welcome everybody to this meeting to kind of hang out and just have a very casual, fun time to be together, especially since the holidays are upcoming. Okay, last item to mention is you may have seen on the calendar that the date for our annual banquet has been set. It's January 11th, 2025. We're working on a super exciting venue, and we have our favorite treasurer to take the mic right now to tell us about the featured speaker that we're really excited about. So Mike Cheeson, if you're out there, please take the floor and let us know what's happening
Will
with our
do.
featured
Thank you. Thank
speaker.
you, B.
Dave,
I think I'm
jump two
the,
slides ahead.
what's that?
I was asking Dave to jump. There we go. 2 slides ahead.
There I am. You can hear my dog going berserk. He's super excited about this speaker that you can see here, Adam Block. I'm going to send a link to his website, not the Adam Block Studios. You can certainly go there. That's the one to learn how to do PixInsight processing. But that's not the reason why he's going to speak at our banquet. The reason why is because this guy has won 99 APODs, 99 astrophotos of the day. That is amazing. For those of you who aren't aware of what that is, that's like, I would say, the highest honor for an astrophotographer. It means NASA picked the picture you submitted as the best one they got. Okay, that day. But still, it's pretty cool to get it. He is an amazing imager. He's an amazing lecturer, and just an all-around great guy. Let me say a little bit more about what this lecture is and is not. We're going to talk a lot about the aesthetics of the night sky, the beauty of it, how to share it. What this is not going to be is a lecture on how to use PixInsight. We are not going to discuss the best filters in Photoshop. In fact, we're not even going to say anything that starts with the letter P, okay? It's all about the beauty of the night sky. So if you are super excited to learn more about PixInsight, that's awesome. That's not what we're going to do here. But if you want to see some absolutely amazing astro imaging images, or just come meet Adam Block, please come to the banquet. We should get out a teaser announcement very soon with the location. It's not going to be the Handlery. And it's also not going to be as expensive, but it's going to be a little bit bougie. I'll say it. It's going to be a nice place, but we've worked hard to control the cost. So I think you're going to have a terrific time. Looking forward to seeing all of you there, and come and meet Adam. Are there any questions for me?
If there's any questions for Mike, go ahead and open your mic or put it in the chat.
All right. I think I nailed it.
Everybody's stunned.
All right.
Thank you, Mike. I'm so excited about Adam. This is going to be great. Okay, next slide, Dave. Couple other items that you've seen before, but we're coming up now to the deadline. We are looking for a new SDAA logo. As you can see on the screen, these are our OG designs. They're not going anywhere, but we thought, next slide, Dave, that we need some improvement, particularly with our letterhead, which looks like this right now. So I have to tell you, I've already received one really cool design from a member that will be obviously considered for either a patch or new sticker, letterhead. Next slide, Dave. What we've seen is that other astrophotography clubs on the internet have some really cool ideas that you can see on this slide. They sometimes highlight something special about their club or the area that they're in. They're super colorful, they're ultra cool, and we want to be like that. So next slide, Dave. Please send your entries to vp@sdaa.org. That address is also on the website. The winning design will either be featured or revealed at our banquet in January. Again, proposed uses, letterheads, letterhead stickers, patches, and the deadline to submit your design is the end of December. Now, as you can see, since our banquet date is set, it's coming pretty close. So just know that your design doesn't have to be perfect. We might even ask a graphic designer to put the finishing touches on it if you desire to do so. So please get your designs in the next couple of months to be considered for our new updated logo. Okay, next slide, Dave. Another thing on our calendar that we've talked about is that thank you all to help elect our nomination committee members. Congratulations, Mark Smith and Dorothy Wood. They are elected as nomination committee members for the 2025 Board of Director election. Next slide, Dave. So what does that mean? Essentially, that means that Mark Smith, Dorothy, and myself as the chair will be collating all of the nominations put forth by the membership if they're interested in running for these positions. What positions are open? Well, 4 directors serve 1-year terms, so all 4 of those are up for election. Bear in mind, too, that there is also incumbents that may be interested in running. So if you're interested, those 4 director positions are open. Also, our president, our recording secretary, and also our treasurer. So these are a lot of key positions that will be up for election in 2025. Next slide, Dave. If you know somebody who's interested or you yourself are interested, here's some guidelines. Be willing to commit the time. It does take some time when you're on the board, at least to attend the business meetings, and then we encourage you to participate in the various committees that the board runs. What are those? Check them out on the website. They're not only identified, but also the chairperson that runs those committees. Be a member in good standing, and what that means is have your dues paid. Don't be delinquent in your dues. It'd be nice to have a track record or volunteer service with the club, although it's not required. Possess needed skills and expertise that you think might enhance those that are already on the board. And probably most importantly, we don't want a bunch of people just nodding yes at these meetings. We want you to be an independent, critical thinker. Yet at the same time, you have to be compatible with your other board members, because at the end of the day, we've got to make decisions in the best interests of the club. So how do you announce your candidacy? Next slide, Dave. This is what the committee has decided. All members interested in running for the open seat should send an email to, again, the vice president at sdaa.org. That address is also on the website, on the contacts page. And at very minimum, your email should include your name, experience with the club, and your vision for our future and how your skills will help us get there. it's not a problem if you want to write more about yourself and why you think you'd be a good fit for the board, but at the very minimum, we ask that, of course, you include your name, experience with the club, your vision for our future, and how your skills will help us get there. The election is actually at our in-person gadget night, November 2024, but there will also be online voting that I think, correct me if I'm wrong, David Decker or board members, the virtual ballot will be open a week after our November 20th meeting for the final votes, but we'll also take nominations from the floor at that meeting. We really want to encourage active participation in our election. Next slide, Dave. And now I'd like to welcome to the floor our former Vice President, Ken Searcy, who has the honor of introducing our featured speaker for tonight, Dr. Andy Boden. Ken, are you out there? Maybe I went too fast for Ken.
He's on mute.
There he is. Hey, Ken, you're on mute.
Hey, you muted me, you dogs.
There you go.
Okay.
Wait, Ken.
Yes, let me begin by saying most people all in the club already know Andy, especially if you volunteer as a docent at Palomar Observatory, and I encourage more people to do that. He is the Deputy Director for Caltech Optical Observatories. That is the organization that controls Palomar Observatory and the Caltech share of Keck Observatory. He has a Ph.D. in high energy physics from UCLA. I believe that means he's a stellar astrophysicist. He also has a master's in physics and a master's in electrical engineering. So with all of those credentials, he's going to give us a phenomenal talk on something we typically don't hear about, which is stellar interferometry. So without further ado, let me turn it over to Andy and turn the meeting over to him as well.
Okay, thank you, Ken. So I appreciate that very kind introduction. Ken and I have known each other for a long time now, I think a dozen years. And he and all the Palomar docents have been great friends to the observatory. And so we're very, very humbled and grateful for their service to the observatory and helping us put our best foot forward. I'm going to try to share my screen. I'm going to be in presentation mode, and hopefully that's what you're seeing as well. So the backstory in this talk is that Ken and I and a number of the Palomar docents went to visit Mount Wilson about a dozen years ago. And, you know, this technology, this description, this technique, interferometry, is how I kind of misspent my youth. And so, as it turns out, Mount Wilson is kind of the birthplace of astronomical interferometry. But yet, when we toured, we didn't hear very much about it. And Ken and I were kind of talking about that, and we decided that we were going to have some kind of geek out session to talk about all that was done at Mount Wilson and what was done at Palomar. And that's kind of where the idea of this talk got started. So I appreciate your time tonight, and hopefully I won't bore you too much. This is an outline of my talk. I am Andy. I'm not Dr. Boden. If you call me Dr. Boden, you will probably confuse me. But if you have questions, please feel free to interrupt me. And I've got some pre-programmed breaks in the talk, which will be good points at which to stop, take a breath, and talk about any questions or issues that I wasn't very clear about. So this is an outline. First, I'm going to try to motivate why we care about devices that we call interferometers and how that came to be. The second section is how we go about expressing interference in light from the sky. And then the last part will be the arc of interferometry at Mount Wilson and at Palomar, where we talk about, you know, some of the things that we did when I was much younger than I presently am. And then I'll try to wrap it up and draw some connections with what we do and what you do, because I think they're very complementary. And I think there's a lot of aligned interests here. Okay, so jumping in, section one. So I'm going to be unapologetic. I care about stars. Stars are what get me up in the morning, metaphorically and literally speaking. And the way I kind of capture that, think about that, is that stars, either individually or in ensemble, are the fundamental observable objects in optical astronomy. It is therefore vital that our understanding of stars be as reliable and as empirically tested as possible. And that's a very motherhood and apple pie kind of statement that you would lead a proposal off with. This is kind of the corollary. In the practice of science, it's vitally important to assert that what we can actually measure is of vital importance. It certainly helps with employment continuity. I want to show you this visualization, because not necessarily because it's all that germane to my talk, but it's a beautiful visualization, and it gets across the point of what we're trying to do in studying the stellar populations. So this is a visualization put together by ESA and STSCI. It starts with imaging of the famous Omega Centauri globular cluster, and it zooms in and just takes a field in the center of Omega Cen. It takes the stars and it sorts them first by color. So blue on the left, red on the right. And then when it's done with that, it'll sort the stars by brightness. Bright on the top, dim on the bottom. And what you see when you're done with that sorting is what we call the Hertzsprung-Russell diagram. I like to think of it as the silverware drawer organizer of stellar astrophysics. It helps us understand what stars are doing at various stages of their lives and how they work. So I'm going to talk about a number of these different classes of stars tonight in what we're doing. So I've mentioned interferometer. I haven't defined it yet. Let me do that. An interferometer is a device that expresses the interference of wave-like phenomena and measures properties associated with that interference. This is often done with electromagnetic waves, but it doesn't necessarily have to be. You can express interference in lots of different wave-like phenomena. Interferometers are often used to make measurements of high precision, and that's usually taking advantage of the small, for instance, 500 nanometer green wavelength of light. LIGO is a perfect example. It uses lab lasers to make extraordinarily high precision measurements of the strain as gravitational waves pass the Earth. My short list of famous scientific interferometers is here. I'm going to talk about a couple of these. First is Young's double slit experiment. You would have heard about this as a physics student, and it conclusively demonstrated the wave-like nature of light. Notice I didn't say that light is a wave, I said it's wave-like. Michaelson-Morley experiment, that was the lack of detection of Earth's motion with respect to the punitive ether, and that led very directly to Einstein's special and eventually general theories of relativity. And then finally, the Michelson-P stellar interferometer, and that made the first measurements of apparent stellar size. I'm going to talk about that next. Specializing, astronomical interferometers are interferometers that create and express interference and measure it from light that we see from the sky. So that's what I'm going to call an astronomical interferometer. And we typically do that in order to obtain information at high angular resolution, higher than can typically be obtained with filled aperture telescopes. Think the Palomar 5-meter or even HST or the James Webb Space Telescope in space. I've depicted the VLA, which is near Socorro, New Mexico. If you don't recognize it, perhaps you'll recognize this picture, which is taken from the movie Contact. To give you a sense of scale, I put together this kind of linear demonstration of the different apparent size scales that we're going to talk about tonight. On the left-hand side are size scales that we're typically used to thinking about imaging with our eyes or with filled aperture telescopes. A common unit of angular resolution is, of course, the arcsecond. I'm imagining all of us know what an arcsecond is. And so when we look at objects that we can resolve with our eyes, we can see, like the moon or the Pleiades, those are typically a few degrees down to half a degree on a side, and that's in the tens to hundreds or even thousands of arc seconds. Jupiter is something that you probably image all the time with your telescopes. That has a typical angular size of 40 arc seconds. So that's this point right here. But when we want to push below the atmospheric seeing limit, or even the diffraction limit of our telescopes, we have to work a little harder to get at the information that's contained at these smaller size scales. So the images I've shown on the bottom of the slide are examples of that working a little harder. This first picture is actually taken from Keck, and it's an adaptive optics corrected image of a multiple young stellar object system, V773 Tau in Taurus. But the rest of these images, these are all obtained interferometrically. So using kinds of devices that we're going to be talking about tonight, doing a program called synthesis imaging or parametric imaging. I'm going to show you some examples of all of that as we go along. What got me thinking along these lines of this presentation is back in May of 2019, I attended a meeting at the Carnegie Observatories of Pasadena. That was the parent organization of the Mount Wilson Observatory. I'm assuming everybody knows what that is. And in the lobby, there is a model of what some people call the most famous telescope in all of optical astronomy, the Hooker 100-inch telescope. It, of course, is where Hubble rediscovered cosmic expansion. But I found the model really remarkable because you can see it's not just the telescope, but there's this weird thing stuck on the front of it. And that weird thing happens to be the Michaelson P's interferometer boom. Now, the 100-inch is the crown jewel of Carnegie's astronomy history. And I found it completely remarkable that they would have chosen to represent that crown jewel with this interferometric boom on the front of it. I think that's incredibly significant, and I'm going to try to tell you why. 100 years ago, we didn't know very much about how stars worked. And that's what framed the questions that led to the incorporation of the interferometric boom on the 100-inch telescope. When Hale set out to evangelize the prospects of larger telescopes, he himself listed stellar apparent diameter measurements that were made with the 100-inch among the most notable accomplishments of the telescope. And that's even after cosmic expansion had been found. So why was he so enthusiastic about that? Well, we see the sun as a resolved star, but for about 200 years, astronomers had been frustrated trying to resolve other stars. And that's because they lacked the necessary angular resolution, mostly because of atmospheric seeing, but also because the telescopes just weren't big enough and you couldn't beat the diffraction limit. So why do you care? Well, stellar angular diameters are the only way to directly measure the surface brightness of stars. And it turns out to be an incredibly important quantity about how stars work. When you think about what a star does, it makes energy at its core and it radiates it from something that we call the photosphere. And for the star to be in equilibrium, those two amounts have to be the same. And so measuring the surface brightness of the star is kind of a proxy for indirectly measuring the energy production in the core and trying to figure out what the physical processes involved are. Now, I'm probably going to slip up in my talk, and I'm going to talk about surface brightness in the language that astronomers often do, which is called effective temperature. Effective temperature sounds thermodynamic, and it almost kind of is, but it's really just an indirect encoding of this fundamental parameter surface brightness that we're trying to get at with these angular diameter measurements. So how did they do it? Well, among other things, 2020 was the centennial of the famous Michaelson P's first measurement of a stellar diameter made on Betelgeuse. And Hale himself went out of his way as he was building the 100-inch telescope to recruit Michaelson from the University of Chicago to bring him to Mount Wilson to work on this very problem. Now, Hale, as you might have imagined, or perhaps already know, was a big enthusiast for stellar astrophysics. And so this was very much on his mind about having Mt. Wilson and the telescope make a significant impact in what was a long outstanding problem in understanding how stars worked. If one goes back a couple of years, Fizeau and Michaelson published theoretical papers explaining how an interferometer might work to measure the apparent diameters of stars. And I'm actually taking on the right a cartoon from that first measurement paper. First author is Pease, in showing the experimental setup. So what you're seeing there is a cartoon mock-up of the 100-inch telescope with that same interferometer boom on the front. And what's shown is a schematic of light coming down from the sky, from a star, and being picked up by mirrors M1 and M4, and then routed in a periscope design down the optical axis of the telescope, where it would eventually be imaged in an eyepiece. And so an observer would actually look at the output from this combined optical system, and notionally, they would see something like this. So hopefully, if the telescope was well focused and the conditions were good, one would see the area rings of a well-corrected telescope, giving you close to the diffraction limit for the star. But on top of the area rings, as depicted in this visualization, would be these alternating areas of light and dark interference from the two optical beams coming originally from that M1 and M4 mirror. And those constructive and destructive zones of interference would overlay themselves on top of the disk of the star, as one would view it. And the measurement would be made based on how visible or not those fringes appear. The method intended to take the mirrors M1 and M4 and move them. So the idea would be, at close separation, one would find the fringes and then generally increase the spacing until those fringes disappeared. And it turns out that there is a well-defined theory about when you'd expect those fringes to disappear. Michaelson had derived it back in the 1890s, and it looks something like this. So this is a plot of the expected visibility of the fringes as a function of a weird variable, the wavelength over the apparent size of the star. But you can trade that in for the separation of those two mirrors, M1 and M4. And the idea was you'd find the fringes when the visibility was high. I need to use my pointer here. You'd find the fringes when the visibility was high, and then you'd increase the spacing and find the place where the visibility disappeared. The fringes disappeared. And that would be your observable that you would then decode into computing the apparent size of the star. So this was first done successfully on 13 December 1920 on, as I said, Betelgeuse, Alpha Orionis. And that measurement led to an apparent diameter of 0.047 arcseconds or 47 milliarcseconds, which is very, very close to the right answer, what's commonly thought of as the modern correct answer for Alpha Orionis. And the people in the dome, which were Francis Pease, and an observing system, they were so excited that they called up Hale, and then they all broke off and celebrated by going back to the monastery and drinking hot cocoa. That's literally in the paper. They described that sense of excitement. But within a week, this was such a big deal that Hale himself had sent telegrams to essentially every major astronomy institution in the world that the problem of measuring the apparent diameters of external stars other than the sun had finally been solved. Pease continued to work at this process for the next decade. And he later published 6 more apparent diameters of giant stars. And Anderson and Merrill, Ken, that's the same John Anderson from the Palomar creation story, also published interferometric relative astrometry measurements on the giant binary Capella. I'm imagining all of you recognize all these names. So that's kind of the first arc of our story. That's kind of the Mount Wilson astronomical imaging, astronomical interferometry origin story. And so now's a good time to take a break and for me to take a sip of tea and ask if anybody has any questions.
I might jump in and note that Albert Michelson was the first American to win a scientific Nobel Prize. He's an Academy graduate, Naval Academy
I was
graduate.
going to ask, where did he teach?
Yeah, he was a Naval Academy graduate, who's a professor at the Naval Academy, and West Point doesn't have a Nobel laureate.
Thank you for that shameless plug, Ken. Yes, Michaelson was a graduate of the Naval Academy. He taught there and then went on to Case Western, where he was when he did the Michelson-Morley experiment, and then he eventually ended up at U Chicago after he got the Nobel Prize.
Yeah.
Anybody else?
Yeah, I have a question, Andy. So how did they know the measurement they made was accurate? Was there any other secondary standard, any method?
No, there wasn't. This gets to the question of how did they calibrate their visibilities and the strength of the particular method that they used. Excuse me. Pardon me, I'm kind of getting over something. The strength of the particular method that they used is that it's relatively insensitive to visibility calibration. You're really counting on the fringes to disappear. But no, they were very much working without a net. Nobody had ever done this before. Michelson had tried some of these measurements at Yerkes and been successful working on asteroids. But Wilson and the 100-inch was the first time that anybody had done anything like this with stars successfully. And so they didn't. They just said, right, this is what we measured, and this is the result that it would imply. And as happenstance would go, it was very, very, within 10% of what is commonly accepted as the right answer. So they were good experimentalists, and they were right to trust their data. But they were working without a net.
The theory was pretty good, it turned out, I guess.
As it turns out, the theory was pretty good.
Thank you.
You're welcome, of course.
Dr. Boden, I have a question. Is there a correlation between the effective temperature of the star and the measurements by interferometry?
I'm going to answer that question in the third phase of the talk. But yeah, a large body of the scientific results that scientific results that we have produced have been focused on understanding the effective temperature scale of stars. It's a big deal because without these angular diameter measurements, you're essentially working in an unmoored space. So a lot of people over the course of the 20s up through the 70s spent a lot of time trying to tease this out in various parts of the HR diagram. I'm not going to talk about it tonight because it takes me too far away from the central arc of my talk, but there was a particular seminal experiment in the Southern Hemisphere called the Hanbury, Brown, and Twist intensity interferometer, which was particularly key in anchoring the effective temperature scale for stars that are solar-like. So yeah, it was incredibly important and cannot be emphasized what a big deal it is.
Thank you.
That is, at least if you care about stars. Okay, are we ready to move on?
Well, at the risk of being obvious to everybody else, but why? I don't understand why moving the mirrors apart causes the fringe to disappear and what's really happening. I mean, I can imagine the fringes fluffing out when the angle between the two wavefronts is 0, but you're not changing angle.
So what's actually happening as one moves those M1 and M2 mirrors apart is you are resolving with a larger aperture and eventually over-resolving the stellar disk. And I'm going to have a couple of slides coming up in this next section that will give you more insight into what's going on. Okay?
Yeah, I just wonder why the fringes disappear.
I hope to show you that.
Yeah, thank you.
Or at least I'll show you where the math comes from.
Okay.
Okay. So in this next section, I'm going to need to start by telling you a little bit about what light is. In order to figure out how one goes about building an interferometer, you need to know a little bit of something about light. So maybe I'm assuming most of you are imaging enthusiasts, at least that's what it sounded like at the start of our discussion. And you know, and I'm going to use some scare quotes here, you know that light is a wave. Because all good imaging enthusiasts do. But in 1690, there was in fact a raging debate. It had nothing to do with these two guys who looked like they're refugees from 80s hair bands, but instead, it was between Huygens and Newton, who were arguing about the fundamental nature of light. So Christian Huygens argued that light was made up of waves, like sound waves, whereas Newton argued that light was made up of particles. He called them corpuscles. And because Newton was a celebrity and Huygens was largely unheard of, Newton won the argument. People largely ignored the arguments of Huygens. It's kind of like taking healthcare advice from famous celebrities on TV, taking their word for it because they're well known. But you might stop me and say, well, wait a minute. We've heard that light's a wave my whole life. So how did this all get turned around? Well, thankfully, Galileo taught us to be empiricists. And in 1801, this guy named Young decisively ended the debate in Huygens' favor with his famous double slit experiment that I'm going to show you in a couple of slides. And for the next 100 years, with the development of electromagnetic theory, people congratulated themselves. We finally understand light, and everything is settled, particularly with the Maxwell theory. That is, of course, until Planck got the whole thing stirred back up again on the next slide. So 60 years after Young, James Clerk Maxwell synthesized a convincing classical field theory of electromagnetism. You've probably heard of the Maxwell equations. And that includes explaining light as electromagnetic waves. And in the 1880s, Heinrich Hertz experimentally demonstrated the reality of electromagnetic waves. And so people think, all right, this is all put to bed. We now understand all we need to know. And you, of course, understand that as soon as you say that, something's gonna jump up and bite you. And it turns out that it was Max Planck. And as a young physicist, he was trying to understand the spectrum of what we call black bodies in physics, warm bodies that emit electromagnetic radiation in a spectrum of different colors. He was trying to come up with a theoretical explanation for that. And that had been a thorny problem for about 15 or 20 years. And I want to say it was in 1898, Planck was struggling with this problem when he hit upon the idea, well, maybe if I treat light as if it comes out in discrete little packets, as opposed to a continuously variable amount of energy, that'll help. And so the story goes, within 24 hours, he had the problem solved. And he was pretty excited about that. Now, the way Planck looked at it, he looked at his quanta as merely a mathematical artifice. It was really a way to get to the right answer. of explaining the black body spectrum. And it actually took another 6 years and some additional experimental results for Albert Einstein to recognize that Planck's artificial light quanta, they're actually real. If you've heard of the photoelectric effect, that was kind of the key additional piece of information that helped Einstein realize that his friend Max Planck had solved the problem. He wrote this paper in his miracle year, 1905, and for it, Einstein won the 1921 Nobel Prize. Yes, that's right. Einstein didn't get the Nobel Prize for relativity. He got it for light quanta and that realization. So quantum mechanics developed for the next 40-ish years, and it took about until the early 1960s for these guys, Feynman and Schwinger and Tomonaga, to put together a practical, that's in scare quotes too, quantum field theory of electromagnetism called quantum electrodynamics. I'm not going to talk a lot about quantum electrodynamics, but at some point somebody should ask me the question, which arm of the interferometer does the photon go through? I want to go back to Young's double slit because everybody needs to get this physical picture in their head about what we're trying to do. So in the Young's double slit experiment, light is incident, in this case, from the top. It comes in, it's a quasi-plane wave, and it encounters a screen with two small holes. Light emits from the holes, and it does disperse out, and that causes these light patterns to overlap. And if you were to put a screen on the bottom down here and measure the intensity of light, what you see is the imposition of the screen with the two diffracting slits creates an intensity distribution of what we call fringes. So areas of bright and dark. And that comes about because you've got the light from these two different slits, and they're going to interact with each other, and they're going to interfere. That's easiest seen in this kind of animation with water waves. So if anybody knows the channel Veritasium, I stole this from Veritasium. But you can see areas where when you've got two sources of water waves, there are areas where the waves add up constructively, and there are areas of where the water waves add up destructively, and you can see the troughs in between the constructive zones. That's basically the same thing that's going on with the Young's double slit experiment. And it's, of course, this wave nature that the experiment demonstrated, which, as I said, conclusively tilted the debate in Huygens' favor. Unfortunately, Huygens was long dead, so we never got to enjoy the victory very much. But at least it settled the question for a little while. Now, if one were to try to take this phenomena and turn it into an astronomical device, it might look like this. This looks an awful lot like the kinds of interferometers that we build. It's a little more generalized than the system that Michaelson and Mt built. But the key elements of it is that one samples the radiation from a source on the sky, S, with two discrete collectors. You might want to call them telescopes. You transport that radiation to a common location, and you combine the light and measure some aspect of it if you're able to express the interference. In general, unlike the Michaelson setup, in general, a system like this can look at sources that are off the optical axis, that are not perpendicular to that vector B. And that leads to the fact that some of the light will get to collector X2 before it will get to collector X1. There's this extra path length. Now, with about 2 pages of math, I can convince you that in order to make fringes from this light, you're going to have to take that external path that just geometry gives you in that X1 arm and compensate for it by adding exactly the same amount of path delay on arm X2, so that the light from the source through X2 to the combiner and through X1 to the combiner travels essentially the same distance. And again, I'll say that again. That matched path length condition is forced upon you by being able to form fringes over finite pass bands in frequency or wavelength, which we always do, right? We always deal with finite pass bands in astronomy. So about this point, somebody's going to ask me, so what does this interferometer actually measure? Because I've just talked in vague terms, so I'm going to define it for you. Interferometers express interference as interference fringes. These are variations in the detected power as a function of the relative path difference between the two arms of the interferometer. That was true in the Michaelson piece setup as the light went off axis. So if you think back to that cartoon in Michaelson and Pease, you had fringes superposed relative to the area pattern, which is centered on the optical axis. So as you went off the optical axis, you had these fringes, and that's the same thing as having a relative path difference. Or an interferometer like the VLA, or the one I'm going to talk about at Palomar, we quite intentionally modulated the optical path difference between the two arms in order to create this change in detected power. But that's what the interference fringe is. It's literally this variation of power as a function of path difference. We typically describe the strength in a power of these fringes in a power normalized sense. That's how Michaelson defined it. And we use this term visibility. We borrowed it from Michelson's original construction. So when the visibility of the fringes is 1, that means that the fringes are oscillating with the full detected optical power or infrared power or radio power of the source that we're actually collecting. And when the variations in power are lower than the total amount of power being collected, then we say that the visibility is reduced. And this gets back to the question that someone was asking me. When an interferometer resolves the source, what happens is the visibility of the fringes decreases. So what was happening in the Michelson P setup is that when the M1, M4 was under-resolving Betelgeuse, the intensity of the fringes was high. It was going from 0 to 1 in a power normalized sense. But as they moved M1 and M4 apart, you were resolving the source structure, and different parts of the source structure were coming in and kind of filling in the power in between, and that's what actually causes the fringes to decrease in visibility. In what follows, I'll be talking about visibility in a power normalized sense, so it's defined in a range of 0 to 1. All right, everybody hold on to your chairs. Here comes the one slide with an equation on it. So for the purposes of my talk tonight, it suffices to say that there exists a method to compute the expected visibility from source properties. That method is given a name. It's called the Van Sittert-Zernike theorem, and the theorem itself is easy to state. The source visibility function is given by the Fourier transform of the brightness distribution on the sky. Now, that statement doesn't provide any physical insight. It doesn't provide any necessarily physical insight into why, as you resolve the source, the visibility goes down. But for right now, I'm going to ask you to trust me and say that's what the math shows, and that's what that equation will give you. If we have some questions about this topic, we can come back to it in the Q&A. But we can, for now, kind of move ahead and not get bogged down in the mathematical details. So now is a good place to break. It's the end of my second session. Do we have any questions? Okay, I'm going to try to get you all out before too long, so let's kind of push ahead. As I mentioned, Mount Wilson is astronomical interferometry's birthplace and has a long history. in this. I'll mention it here just for completeness. I've already talked about the Michaelson and Pease experiment. Pease went on to build a 50-foot interferometer that never did a whole lot for kind of reasons that we understand a posteriori. MIT and US Naval Observatory built optical interferometers on Mount Wilson. Berkeley built an installation. And in present day, the Georgia State University Char Array is the world's largest near-infrared interferometer that operates. It has operating baselines up to about 450 meters. And that allows us to get to unprecedented levels of angular resolution, at least in the near infrared. Of course, Hale, pardon me. Of course, Hale, having finished Mount Wilson, was moving ahead with developing Palomar, and he was in salesman mode. And in that process, Hale, because he was an enthusiast for the science, he anticipated building an interferometer on what it was eventually going to be the Hale telescope. This is a direct quote from a report that he wrote to the sponsoring agency for the Palomar building, the Rockefeller Foundation, where he says, it comes out and says it, among the science that we are most excited by is the idea of another stellar interferometer boom on the front of a telescope that should be rotatable, and that'll allow us to get to lots of different stellar diameters, and in particular, measuring separations of spectroscopic binaries. That's going to be a topic I'm going to come back to. No less an authority than the astronomy historian Dave Dvorkin has come to be convinced that, and make the argument, that interferometry was, in fact, Hale's motivation for building the 200-inch telescope. I've taken this quote from a Britannica biography, but I'm going to read the pertinent sentence in here. Quote, since the diameters of even more stars could be measured with a larger telescope, Hale was convinced of the scientific necessity for larger telescopes. He expresses a causal relationship between Hale's enthusiasm for the interferometry that was done at Mount Wilson and his desire to push on further to build the 200-inch telescope. Now, of course, Hale passed before the 200-inch was completed, so he wasn't there to see and make certain that that vision for the interferometry boom was realized, so it never was. But in the period of the 70s to the 90s, people tried to do interferometry experiments on the 200-inch telescope. I've got a list here. I don't need to walk you through it. I'll just mention it, the list here for completeness, although there's some very important astrophysical results on this list, if anyone wants to come back in the Q&A and talk about them. Now I'm going to talk about my interferometer, what I misspent my youth doing. I'm going to start with some panoramic pictures. So this, of course, is an idealized view of Palomar Observatory. I'm assuming that everyone or most of you are familiar with it. And you can see the major telescopes on site and additional buildings that were added in the mid-90s. That is, of course, the development of the Palomar Testbed Interferometer. PTI was a long baseline near-infrared interferometer that operated at Palomar from 1996 to 2008. The objective was actually technical demonstration, and NASA funded the development in order to retire certain technology risks for future larger investments, in particular, the investment in the Keck interferometer. What was novel about PTI relative to its predecessors it used control techniques. So this will pick up the ears of the electrical engineers in the audience. It used control techniques to operate highly efficiently, by which I mean it made more quality measurements per unit time than any interferometer before and essentially since. Even that interferometer in Mount Wilson, Chara, makes far fewer quality measurements per unit time than PTI did in its heyday. But I'm happy to say that when nobody was looking, we got to do some fun science with it. This is a picture from National Geographic. It's a very photogenic picture of the interferometer and the Hale telescope behind it. And it gives me an opportunity to show you a plan view of the interferometer. And the idea was that light would be collected at these small outrigger installations. We called them siderostat huts. That light would be injected along these beam pipes into the central combining area. The majority of the space in the central combining area was taken up by these delay lines. Remember, I talked about equilibrating the internal delay and the external delay for sources that were off axis. So that's just a practical necessity in order to measure the fringes over a finite passband. And once you had corrected for the delay, light was routed here and here in order to accomplish the combination. Here are some terrible 90s electronic pictures. I apologize. So this is a picture down the long delay line axis. And this is in some sense the T in PTI. Again, I'm going to speak to the double E's in the audience. These were really remarkable multi-stage actuators that did some amazing things. They had spatial dynamic range over 9 orders of magnitude in space, and temporal dynamic range over 4 orders of magnitude in time. They needed to move in real time systematically because, of course, the Earth rotates, and so it moves that delay balance aim point on you as in real time. And then, of course, the atmosphere is turbulent, twinkle, twinkle, little star. So all of these problems added up to a challenging dynamic control problem that these things were just a technical tour de force. There were 3 different stages of actuation, but I'm probably waxing rhapsodic too much already, so I'll move along. But maybe a double E or 2 in the audience will want to circle back and ask me about this stuff. Now, of course, once one had equilibrated the delay, one had to do something with the combined beam, and that's what this very busy optical table was all about. This is a terrible 90s photograph, and it shows where we combine the light. On the lower left is the schematic, and what I'll call your attention to are these 2 optical axes, A and A prime. That's where we would inject the light that we would collect from the 2 different telescopes or siderostats outside, and we would bring them in parallel, and with an arrangement of mirrors, we would superpose these 2 separate optical beams on this optic beam B3. B3 was a 50-50 beam splitter. Now, all of this is disassembled. I can't show you what this beam combiner looked like. But what I can show you is the optic B3, because I've got it right here. So I got to keep this. This was kind of my prize for becoming deputy director of the observatory. This is literally the 50-50 beam splitter that was used to combine the optical fields from the 2 separate arms. As you can see from the diagram, those 2 optical fields were counterpropagated onto the optic, and then the combined beams would then propagate away from the optic and then be routed into a dewar with an infrared detector here in gold in the picture and in this circle here on the schematic diagram. But incident on beam 3, you had 2 separate beams from 2 separate collectors. Propagating away from beam 3, you had 2 combined optical beams. So the interference happened at this optic right here. And everything else was just detecting the radiation. How did PTI see this guy? Well, we used to look at these plots. They would come out and be in our email every morning, and we would describe them as an example of a plot only an interferometrist could love. because it's a bunch of points as a function of time. But this was music to our eyes. This told us the story of how the system had run over the course of the night. In our scheme, the unresolved sources, we would intentionally measure sources that would be unresolved to the interferometer, so as to measure the point source response of the interferometer. And all of these sources that you see up here at a visibility of V squared in our nomenclature of 0.75, those are all measurements of the point source response of the interferometer. You can see it would change over the course of the night as conditions changed or alignments might drift. So it was important to keep up with how things were changing. But the sources with V squareds less than 0.75, going back to the question about Michaelson and Mt, those are the sources that are actually being resolved by the interferometer. And I've intentionally chosen a particular night where a lot of my sources were being observed, not just because they're my sources, but because I've looked at a lot of binary stars, and those are, of course, forgive the language, non-axisymmetric sources. The reason these visibilities are changing systematically with time, some going down, some going up, some oscillating, is because what's happening is the Earth's rotation is changing the baseline projection on these two sources. And so you're seeing the effects of changing baseline projection on the non-axisymmetric sources that we're looking at in this night. I'm happy to say that we're still publishing data with PTI. This kind of cyan line is a paper that just went in to the AppJ not 3 weeks ago. So we're still mining this. We're still mining this database for hopefully relevant astrophysical results. So what did we do with this data? Well, we did the same thing that Michaelson and Mt did. We measured a lot of apparent diameters and thereby effective temperatures of hundreds of evolved stars of every conceivable persuasion: giants, supergiants, Miras, carbon stars, pulsating, all kinds of different zoology in the evolved star cornucopia. And here's an example of a plot from a paper from a few years ago led by my friend Gerard Van Bell of a very large data set of giant stars. And we were talking about the importance of defining effective temperatures. So here's an example where Gerard and his collaborators are focusing on constraining effective temperatures as a constraint on the evolved stellar atmospheres in stars as a function of this empirical color index in the visible and the color difference in the visible and the near infrared. And again, repeating what I said at the start of the talk, these surface brightness measurements help us constrain exactly how these stars work. They're a very important part of constraining our models of how stars actually function. PTI also measured a handful of diameters for main sequence stars, the most notable of which I'm going to show you next. So this is Altair. You are imaging enthusiasts. All of you know Altair, or Alta Aquila, Alpha Aquila, as one vertex in the summer triangle. But I'm a knuckle-dragging physicist. I know Altair as a rapidly rotating A7 main sequence star. It rotates so rapidly that it is what we call rotationally oblate, or paunchy, as astronomers of a certain age tend to get. And PTI made the first direct resolved observations of stellar rotational oblateness with Altair, published by Gerard and collaborators in 2001. This was a big deal. Nobody had ever done it. We kind of expected, in fact, the theory of how this was supposed to work was known back as far as the 1920s, but had never been empirically demonstrated before. Chara and the VLTI have done a number of additional measurements in this space. This is a list of stars from my friend John Monnier, who built the Merck beam combiner that still functions to this day at Chara. And I think the key addition that Merck has added is they've actually measured changes in the apparent brightness, the apparent effective temperature changes in these rotationally oblate stars at the pole and at the equator. They're different. That was expected. That was a part of the von Zeipel theory, but no one had ever seen it before, and it was very well demonstrated by the work that Chara added as a follow-on to the work that we did with PTI on Altair. I'm going to talk about one more notable diameter, Zeta Geminorum. So I don't know a lot about Cepheids. I do know that Zeta Gem is a classical Cepheid pulsator. In 2000, Ben Lane and collaborators published the first direct resolved observations of Cepheid pulsations using PTI. So, of course, we've known about Cepheid pulsations for a long time with the Levin law, but no one had ever actually imaged, in this case parametrically imaged, but seen the Cepheids moving in and out as they went through their pulsational cycle. The way this worked is that Ben and collaborators measured the apparent diameter of Zeta Gem over a course of a number of nights, over a few weeks. That's this plot here on the left. And then when you phase them up with the known pulsational period of Zeta Gem, you build a phase curve that looks like the plot on the right, where you can see the diameter expanding and contracting, going through its pulsational phases. This is a big deal. This was our first Nature paper at PTI.
That's interesting.
Okay, about those binaries that Hale talked about. Well, that's kind of how I misspent my youth. I did a couple of tens of these systems, and including ones that we're still publishing with the PTI database. I'll call your attention to one that's kind of fun. 12 Boötis. It's a relatively bright star. It's in the spring sky. And in a couple of publications, we reported on ridiculously high precision dynamical masses and radiometric properties of these stars. Now, what makes this kind of a unique system is that it exhibits a surprising component brightness difference. Roughly 60%. The primary is roughly 60% brighter than the secondary at 2.2 microns, despite the components being nearly equal mass. And I will admit, I spent several days walking around muttering to myself, how can that possibly be? Until we finally figured out that this is real. This is not a mistake. This is not a brain cramp from my code, but it's a real effect of the primary evolving off the main sequence and entering a phase of stellar evolution called the Hertzsprung gap. It's thought to be rare because the stars shoot across the gap very quickly. So it's unusual to find stars in this particular spot on the HR diagram, but it was kind of unique. Well, it was unique and exciting to be able to pin down the dynamical mass and radiometric parameters for such a star and constrained models of how stars make that transition from the main sequence, the end of the main sequence, onto the red giant branch. One last scientific highlight, and then I'll try to wrap up. PTI and young stellar objects. Operating in the near infrared, PTI came along at just the right time to make first-of-a-kind observations of circumstellar material in young stars and resolving those size scales. And that was really three key results. First was my friend Fabien Malbé, who resolved structures in the very famous, the archetypical famous FU Orionis. It's a prototype. It is the prototype of young stars that are going through very heavy accretion events and are optically changed magnitudes by several magnitudes over periods of years. These are quite dramatic accretion events on these accreting young stars. My friend Rachel, my longtime colleague Rachel Akeson, surveyed and resolved a number of pre-main sequence interdisks around a sample of T-Tauri stars in Taurus in a couple of publications. And that led to some fundamental insights into what the morphology of these circumstellar disks, these protoplanetary disks, might actually be. And then Josh Eisner resolved structure around kind of the higher mass analogs of T-Tauris, the Herbig AEB stars, in a publication in 2024. This was all very heady stuff when it came out, so we were pretty excited. So I'm going to try to wrap up because it's getting late. What is PTI's legacy? If I were to try to capture it, it kind of falls in these four categories. We did a number of technical things for the first time in devices of this character. We did a number of novel scientific things and that excited us and maybe a few other people. It was an interesting sociological experiment. It's always humbling to come to a place like Palomar where so much interesting astrophysics has happened and imagine contributing a chapter to the story. And I think that we did that, and I'm proud of having been a small part of that. And it gave young astronomers or refugees from physics, young refugees from physics, an opportunity to realize their dream of contributing to human understanding of the universe and our connection to it. And that's where I want to kind of bring it back to the topic from the start of the night. I process this in the following way. Astronomy is, in essence, a contribution to human culture, one that's focused on helping us understand our connection to the universe around us. And humans build telescopes and interferometers, or even particle accelerators, to extend our perceptions and explore and experience that connection. And for some people, that ends up looking like providing access to information about things beyond our everyday experience, which is what PTI did, which is what the Michaelson Pease experiment did. For some people, that means providing an emotional connection to those same things. And I intentionally chose an image from HST with Wide Field Camera 3 of the Eagle Nebula. This, of course, is a star-forming region. It's thought to be prototypical of the kind of place that the protosolar nebula came together and where our sun and our planets form. And one looks at a picture like this, and it's impossible not to feel a sense of connection to what's happening on this scale and just our own human reality. A lot of astronomers think they understand telescopes, and they think interferometers, they're somehow mysterious. They're these strange devices that make strange measurements that are hard to understand. But as someone who's spent a considerable fraction of my life doing it, I certainly see them as serving complementary roles by providing complementary information. I've chosen this image on the right as a set of very important synthesis imaging interferometric images made by the ALMA array of protostellar disks. So this is the famous D-sharp sample. It's famous to me anyway. Astronomers, this is a big deal. We all gasped when we saw these images for the first time. These are all stars that are 1 or 2 million years old, and a millimeter wave interferometer called ALMA in the Atacama Desert in Chile has used synthesis imaging techniques to make images of those protostellar disks, same as one we talked about a few slides ago that we started probing with PTI, almost probing complementary information in this region of star formation. And you can see, as early as 1 million years, these disks are already forming structure. The key question in this structure is this a real present sign of planetary formation, or is there something else going on? But this is very much cutting edge science. I process this as these telescopes and these interferometers. They're essentially two sides of the same coin. That they're systems that exploit properties of light that give us access to information that we seek and value. For me, the mystery is not so much the device, but the phenomena that light is, because God is subtle. So I'll leave you with this. Next time you're looking at the sky with your favorite device, think a little bit about your own connection to what you're looking at. And I'll leave you with the M87, the famous M87 image, yes, generated by an interferometer of the supermassive black hole in M87. Thank you very much for your kind attention.
What a terrific talk. Thank you so much, Andy. Please let us know if you have questions. Either unmute your mic, put it in the chat.
Okay, I'll ask one. And you know I love this talk. If the path length difference between your two receiving telescopes is a function of the off-axis position of an object you're looking at, and of course you know what that is by declination and right ascension, can you use that to calculate the path length difference?
That's exactly what you try to do. And then things get interesting. I'm going to go back to a slide. Let me jump out of slideshow mode and go back to this cartoon slide. So you'll see that I can just write down a simple vector equation for what that path length difference is, and then just apply it down here. And that, of course, is what we try to do. That's when we're looking for the fringes. We're using this delta D equals B dot S. And of course, S is a function of time because the Earth has the unfortunate habit that it likes to rotate. Now that gets you in the neighborhood, but then you have to deal with the fact that the atmosphere is turbulent. And so on a seeing timescale, on from 1 to 10 milliseconds, the atmosphere is creating seeing variations in an image plane that looks like image motion and image distortion. In this space, that looks like the atmosphere picking up the fringes and moving them on you. And so it is very much an active search process. And then once you find the fringes, an active tracking process to make certain that you stay on them. And of course, you do that with finite success. So occasionally a big seeing cell comes by and you lose lock and you have to refine the fringes. But that's exactly right. That's exactly what we do, Ken. We take advantage of the geometry that we know to get us in the neighborhood. And then the real fun begins.
How does the path length on the PTI vary with sidereal rate?
I actually had that buried on a slide, right?
Centimeters per second or something?
Yeah, it's moving centimeters a second. So just from Earth rotation, I've got to track the fringes at centimeters a second and then track out what the atmosphere is doing on top of it.
Andy, there's a question in the chat from Dennis. Dennis, I'll just go ahead and read it. Dennis is asking, did you say how fast the star Altair rotates?
Oh,
I didn't. And I should have looked this up. So you can in real time check me on Wikipedia. I remember the rotation period of Altair being something like 12 hours. So somebody type it in Wikipedia and look it up. It's a little longer than the rotation period of Jupiter, but it's very short. It's not that different from the theoretical breakup velocity at the equator. And that's, as it turns out, a pretty common feature for these higher mass stars. So A and B stars are often found rotating near near this breakup velocity, and they're often rotationally ablate. All of those rogue gallery rapid rotators are all, higher mass stars, and we think we know why that is. I'll just throw it out there. We think that higher mass star formation works in such a way, forgive me, that it suppresses the formation of these protoplanetary disks, and we think these protoplanetary disks are a key factor in coupling angular momentum away from the star and into the disk and slowing the star's rotation down. So that explains why, for instance, our sun has a rotation period of 28 days, and Altair has a rotation period of 12 hours or whatever it actually is. Has somebody checked me, by the way? What's the right number?
10 hours. 10.
10 hours? Okay. I was close.
Andy, there's another question in chat. Can you see chat?
I cannot see chat. Actually, maybe I'm about to say something that's wrong. I was about to say I can't see chat and share my screen at the same time, but I think that's wrong. I think I can actually pull up.
While you're looking, Andy, Jim, you can unmute too, since you have more than a couple questions there, and unless Andy finds he has the chat window.
I got the chat window up.
Awesome.
Okay. Yeah, I was just curious on physical size for an interferometer. I've seen the Keck twins, and they're separated by a lot of distance. So I'm wondering,
right.
Is PTI similar?
Yeah, we were actually a little bigger. So I worked on both PTI and the Keck interferometer. I think I actually say the physical size in one of these slides. It's 110 meters. So our north-south baseline. Did I say it? No, I might have put that slide in the backup. But the north-south baseline was 110 meters, and that gave us a 2.2 micron fringe spacing of about 4 milliarc seconds on the sky. The Keck separation was more like 85 meters, so it was similar, but the fringe spacing at K-band with the Keck interferometer was more like 5 milliarc seconds. Okay. So we actually had a little more angular resolution, if a lot less sensitivity with PTI.
Okay,
because our collecting apertures were only 40 centimeters in size. That's a little smaller than 10 meters.
Wow. Thank you.
Excellent question. So there's a question here about the M87 black hole. I'm glad you asked that. I'm going to go back to my cartoon apparent size scale. So I'm going to take a drink before I do them. So the highest angular resolution image that I chose for this demonstration was that M87 cartoon, that synthesis image, I should say, from the Event Horizon Telescope. Now, that measurement, I probably should have looked this up, I apologize. I don't remember the radio wavelength. It was probably centimeters in size. So, a factor of 10 to the fourth longer wavelength than we used with PTI when we're working in the infrared. But the physical size of that event horizon, the apparent size of that event horizon in that image is, I did look this up, 41 microarc seconds. You can see where it appears on that linear chart. So this is far and away the highest angular resolution that people have achieved with interferometric imaging. And that takes, in the case of the Event Horizon Telescope, that takes an interferometer that's the size of the Earth. People are using radio antenna all over the globe and imaging these incredibly small, apparently small structures in M87 and, of course, in our own galaxy with Sag-A star. So you do need to get an interferometer measurement, collect radiation over a very much larger size. Did that answer your question, Jeffrey?
Almost. I was wondering about the, interferometer basically works in linearly, right? It works in one dimension across the object. So do you need to get measurements in a bunch of different directions?
Yes, you do. And I'm gonna pull up this slide, even though I said I wouldn't do it again unless someone twisted my arm. This guy right here. So this is the Van Sittert-Zernike slide. In interferometric imaging, there is this concept called the spatial frequency plane, or the UV plane, and it basically mathematically captures what you're referring to. You have to measure across your source at a bunch of different spacings and a bunch of different angles in order to collect all of the information necessary to invert that Fourier transform and estimate the parent image, like they did in the event horizon or the D sharp, or even the ALMA image of Alpha Ori that I showed. That's kind of a detail I skipped over in the interests of trying to get y'all out on time.
How many
yeah,
for the event horizon?
yeah.
How many detectors are there?
So I'm gonna work from memory, and someone's gonna check me on Wikipedia and find out how wrong I am. My recollection is the M87 event horizon image was collected with 15 telescopes. Is that too many? Maybe it's something like 12. It was on the order of between 10 and 20 for M87 and event horizon. The images excuse me. The images of the D-sharp disks, those are made with ALMA, and ALMA has on the order of 70 collectors. So there's much more spatial frequency information to work with in the ALMA synthesis imaging program than with the Event Horizon telescope. Some of you have probably seen radio images of big bipolar jets in the radio coming out of the VLA. VLA has 27 antenna and a bunch of different spacings. So all of this serves to sample this thing that we talk about called the UV plane. And that's that same U and V in the kernel of that integral transform in order to collect all the necessary information in order to invert this equation and estimate the parent bright distribution on the sky, otherwise image it. Are there any other questions I'm missing?
I don't think so, Andy. I think you covered them in chat. Any more questions from members?
Let me ask one that nobody will ask. We know what you call an astronomer who uses spectroscopy. He's a spectroscopist. What do you call somebody who does interferometry?
Well, you can probably guess it.
Yeah.
An interferometrist. But if I could jump down to that 12 boo slide again, when you're doing work like this, you're really using every tool at your disposal. So when we analyze a physical system like this, we're getting the relative astrometry from interferometry. We're getting the radio velocities from spectroscopy. We're using photometry to synthesize the spectral energy distributions of the stars. And in one of the most recent submitted papers, we're even using radio data and seeing evidence of circumbinary material in a fun system that maybe you'll invite me back to come talk about someday. So when you're trying to really push on and constrain these stellar theories, you're really throwing every tool that we have at these systems and synthesizing it all together. It's not just one technique, but it's really pulling everything together in trying to become the proverbial jack of all trades.
Absolutely, Andy. We'd love to have you back to talk about whatever
You're very kind.
Oh, we need Andy. We need Andy to come back and talk about Russell Porter.
That's right. That was the other talk I could have given.
Any more questions for Andy? Andy,
Okay, I'm going to
thank
stop
you
my
so
share.
much.
Thank you so much
Again,
for your
thank
kind
you.
attention.
Thank you so much.
Thank you, Andy. That was amazing. Really enjoyed it.
Thank you, Andy.
All right, Dave, let's get to our last slides and close this up. Ready for the quiz, everybody? I thought I'd switch gears since I didn't know anything about Andy's expertise. So next slide, Dave. Here's the quiz. If you know the answers to these questions, enter them into the chat. Do not shout them out. First 3 people to answer both correctly win club stickers. Don't forget, please, to send me an email when you're a winner so we can get these stickers shipped out to you.
I know the first one.
That'll get you half a sticker. You need the second one. All right, we've got answers coming in. There's one right answer in chat. Oh, well, okay, I'll count 2. Some of you were half right. We're almost there. One more. Priscilla, Google, please, the answer. Any other guesses before we reveal the answers? There we go. Good job. Next slide, Dave. The answers are Venus and Neptune. Pretty crazy about Neptune. We'll wait for Dave to get the slides back up. While Dave's working on getting the slides back up, the final slide is just a reminder for Gadget Night in person. We have 3 in-person meetings a year. It's a great time to hang out and see everybody's faces in person. So we're working on an awesome venue. We're hoping to have food and drink there, which is kind of what chased us away from Mission Trails. So stay tuned for that news. Gadget Night, November 20th. Okay, I think we can close up this meeting. Thank you so much, everybody, for attending, and for our guest, of course, Andy, for an amazing talk. Hope to see you all guys in person next month.
B, can I make one more quick comment? This is
Sure,
Dave
Dave.
here. How are you? The election, the nominations. This is very important to us this year. B explained the process very well in the beginning of our meeting here. Nominations begin now. Volunteers begin now. Those will be vetted by the committee, and essentially will end up on our election in November. So the election actually begins at the November meeting and will last a week or 2. It will be handled by Election Buddy, so it's very easy to do. We have some experience with that right now. So in the meantime, we are considering the possibility of those that have interested in positions and submit some kind of a bio for themselves. We can post that to the club by way of Wild Apricot, so that the club members can read about you and find out who you are. With 800 members scattered all over the world, sometimes we don't really know each other. So that would be a good thing to do. If you have a good bio, you can submit that, and we'll get that out to the rest of the club, so they have that information for the election in November. So get that stuff out. Be in touch with B, and I look forward to see where this goes. Thank you, B.
Thank you, Dave. You can reach me at vicepresident@sdaa.org. And you can also find that email address on the website under contacts for VP. Any questions for Dave while we have him here?